Good morning. Welcome to NASA's Goddard Space Flight Center and the NASA Social for the blooming partnership between NASA and JAXA, the Japanese Space Agency. Today, we're going to get an in-depth look at the Global Precipitation Measurement Mission, or GPM. I'm Jason Townsend, NASA's Deputy Social Media Manager. Today, we've invited 60 of our social media followers to join us here in Greenbelt, Maryland for this NASA Social. But before we start going into too much more detail, for the benefit of the viewers on NASA TV, just what is a NASA Social? Well, a NASA Social is all about taking the online offline. We invite our followers, our fans, and our social media community members out to NASA facilities to take part in these special events where you can get access to see our facilities and meet our passionate employees that most folks don't really get a chance to do, but you can share that experience back online with the online community out there. So think of these folks as your representatives in this room. We hope that you'll follow along online by following @NASA and @NASA_RAIN on Twitter, or you can like the NASA or NASA RAIN pages on Facebook, or you can follow NASA on Google+. If you want to follow or join the conversation, be sure to use the hashtag for today's event, which is #NASASocial. We're also taking questions online for those of you who are following along and watching our broadcast using the hashtag #AskNASA. Also, for our Japanese speakers today, we're doing something special by taking questions in Japanese using the hashtag #AskJAXA. For those of you unfamiliar with that, that's #AskJAXA. Now, you might ask yourself, why RAIN? Why is this mission's social media accounts called RAIN? We have several past, current, and future missions that measure rainfall around the globe. You'll hear more about this constellation of precipitation measuring missions and the data that they collect during the next 90 minutes. You'll hear from a variety of different folks who each have a unique perspective on this mission, from the hands-on science work being done by both NASA and JAXA, all the way to the big picture of our Earth-observing programs. These speakers are part of this event, the 61st NASA Social Media event. It's experiences like these that really help share NASA with new audiences in new ways, and it gets shared in very non-traditional ways that show off the science and engineering work that we do here at NASA. We strive every day to promote the diversity of amazing work done here and to share our missions, programs, and talented employees in ways that connect with everybody. The NASA Socials are just one part of this strategy, and the strategy is always evolving. We're always looking for new opportunities to connect with new audiences and share information in new ways. We're also exploring where you, the public, is, and figuring out on what social media you guys are going to be connecting with us on. Where is it all headed next? We're on the most popular platforms now, and we're always looking for new and emerging ones. So keep an eye out for us as these new platforms come online. So thank you for joining us for this event today and this experience, no matter if you're here in person or watching online today. Without any further ado, we're going to go ahead and go into a video here to introduce today's topic, the GPM mission.
Only 3% of water on Earth resides as fresh water, and only a tiny fraction of that is actually accessible to us on the surface.
7 billion of us live on this planet. We all have to drink water to live. Where's the water that we drink come from? By and large, precipitation.
GPM is an international satellite mission providing a new generation of observations of rain and snow in all parts of the world every 3 hours.
If you have good precipitation information, you can do a very good job of characterizing drought and often its subsequent impact on agricultural productivity.
There's about one major flood a day someplace in the world. So it's not as if it's a rare event.
Understanding how much snow is falling is important for transportation, safety, how much fresh water falls and is stored in snowpacks. But we really need to focus on all the phases of precipitation so that we know the global picture of where fresh water exists in the Earth system.
Wonderful. We're going to go ahead and get started with our first speaker here. From NASA's Earth Science Division at NASA headquarters, we have Ramesh Kekar.
Thank you, Jason. Good morning. Yes, I'm from NASA headquarters, and I'm program scientist for the TRIM and GPM satellite missions. As the video showed, water is an integral part of life on this planet, and NASA is at the forefront NASA plays a major role at the forefront of water cycle research. Study of the water cycle is important because it creates an understanding of weather, climate, droughts, floods, etc. So here are some examples of the satellite missions that are involved in water cycle research. TRIM, Aqua, Grace, Aquarius, they're flying right now and they're making measurements. GPM, as will be explained later on, is going to be launched early next year, and SMAP, the soil moisture mission, is going to be launched in 2015. So TRIM is a collaborative effort between NASA and Japanese space agency JAXA. It was launched in 1997 as a 3-year mission, but it's still flying and making measurements. Its enormous success led to NASA and JAXA collaborating again on GPM, another precipitation mission. Japan also provided an important instrument for the Aqua satellite, the second one there. So to celebrate this US-Japan cooperation, Cherry Blossom Social is an appropriate theme for today's meeting. One interesting thing I wanted to point out here is, can we move on to the next slide? As TRIM did before, GPM will do an excellent job of measuring rain or precipitation. But the problem is most of the time when it is raining somewhere, GPM or TRIM are somewhere else. So that brings us the concept of constellation satellites. These constellation satellites are cross-calibrated against the GPM core satellite. So even if the GPM core is elsewhere, a constellation satellite that is tuned with the GPM core is likely to be allowing us to make the measurements that we seek. So for right now, this is all I have to say. We'll wait for the Q&As later on, and so on to the next speaker.
Wonderful. Before we move into our next speaker, we've got another video here that talks about some of the water cyclones. So,
this is what we call severe damage. This is the bridge out of town, and we're not going anywhere.
This is the worst flooding Vermont has seen in nearly 75 years. Tropical cyclones, a general term for hurricanes, typhoons, and tropical storms like Irene, don't just stick to the tropics. These storms can charge northward and wreak havoc in areas that normally wouldn't see this kind of extreme weather. Satellites provide us with near real-time information about the intensity of storms and where they're headed. Since its launch in 1997, TRIM, the Tropical Rainfall Measuring Mission, has remained a gold standard in collecting global rainfall data on storms. And while TRIM provides essential information on cyclones for tropical areas, for regions like New England, TRIM simply falls short. The Global Precipitation Measurement Mission, or GPM, is a constellation of satellites unified by the GPM core spacecraft that will provide a global picture of rain and snow every 3 hours. When GPM launches in 2014, it will greatly improve upon some of the limitations of TRIM. In addition to measuring a wider swath of the globe, the GPM core spacecraft will carry more advanced instruments with greater sensitivity. There's the GPM Microwave Imager, or the GMI, a radiometer that will use 13 microwave channels to capture precipitation intensities and horizontal patterns. Then there's the Dual Frequency Precipitation Radar, or the DPR. That uses 2 frequencies to visualize in 3D the precipitation structure from the cloud down to the surface. With GPM's more sensitive instruments and wider coverage of the globe, we can more accurately profile a tropical cyclone, predicting where they're likely to form, how intense they're likely to become, and tracking the path they'll take so that agencies can make better decisions to help get people out of harm's way.
It's really scary to see some of the power of water that's out there. So as you saw with some of the flooding and things that was going on there. Right now, we're getting ready to hear from Dr. Gail Scafronic Jackson. She is the Deputy Project Scientist for the GPM mission, and she's here to tell you a little bit about the science.
Thank you, Jason, and actually thank you for our audience that braved the wet weather and got rain on their head to come out to find out why NASA is building a satellite to measure precipitation from the vantage point of space. So thank you for coming. So you've seen the videos here and why water is so important and precipitation is falling is so important. And I'm just going to give you a couple more details. First of all, you may be wondering, why go through all the effort of building a satellite to measure what you can just put a rain gauge out in your backyard? Well, the reality is if you look at all the rain gauges in the world represented by those yellow dots, and you try to look at those, you can see that most of them, there's not very many over the oceans, but if you were trying to put them side by side next to each other, they would actually only fit on 2 basketball courts. 2 basketball courts does not represent global precipitation. No way, no how can you use that to represent global precipitation. So one of the issues then is, how can we take this data? I mean, why not just use your cell phone to get the weather? So we want to be able to do it globally. One of the reasons to do it globally is because you can't get the measurements over land. Another thing is, well, how is it to measure precipitation from space? How can you do it? Well, the terminology is called remote sensing. Remote sensing essentially means that you're taking a measurement from far away and using that indirect measurement to estimate the actual precipitation or other field that you're measuring. For GPM, it's pretty cool because we're looking at, say, rain over the Statue of Liberty in New York City and measuring it from the distance of Washington, D.C. That's the actual distance between the surface and the satellite. It's about 250 miles. And yes, we can estimate precipitation from 250 miles away. It's great. So if we move on to the next slide, I want to talk about specifically a little bit more details about how these instruments measure. You saw some of that in the video. So as a spacecraft flies overhead from 250 miles, or 407 kilometers if you like to use those units, we have 2 frequency radar that does the 3-dimensional imaging of the cloud. It's like taking a CAT scan of the cloud. We also have the GMI, which is our radiometer, which makes a wide swath that essentially projects all the rain or snow in the column of the cloud and projects it 2-dimensionally on the ground. And so that way you get both a 3-dimensional structure and a wide swath data. And we can use this data to, the radiometer data is more like taking an X-ray. And just like a doctor uses X-rays and CAT scans to diagnose what's happening in your own body, we, for GPM, use the CAT scans and the X-rays of our instruments to diagnose and tell us exactly what's happening within the cloud. This is a way we put together the puzzle of precipitation so that we can understand it better. The other cool thing about these instruments are they measure rain rates from 0.2 millimeters an hour all the way up to 110 millimeters an hour, and they're able to detect falling snow. This is a great accomplishment beyond TRIM. So if we move on to the next movie, which is the Constellation sequence, which you've already seen, GPM is using these advanced measurements from the radiometer and the radar to give us more information about the precipitation. The first thing we want to do to make sure that our precipitation estimates from GPM are uniform across the globe is to make sure that there's no biases in the measurements from one satellite to another, and we have a large group working on that. The second thing is we use that 3-dimensional structure we get from the radar to improve the algorithms the best that we can. And once we improve the algorithms on our core satellite, we can transfer that standard to all of our other constellation members. So in this way, we're able to get rain rates every 3 hours everywhere on the globe. So wherever you live, wherever you've come from, you will know how much it's rained or if it snowed every 3 hours. And this is great for all the societal applications, the floods, the landslides, the hurricanes. We want to know how much it's raining globally. And then we can use that information to improve weather forecasting and climate change models. So now I'm going to finalize. I mentioned when I introduced myself that I love snow. And actually, falling snow research is my second job at Goddard. And I really do like snow. The guys up, Ryan up in the video area, he put this together because I love to talk about snow. Snow is a new challenge for precipitation measurements from space. Most raindrops are either spheres, or you have one of these in your packets. This is what we call our droplet. When it falls, it gets kind of flat. But rain is almost always either spheres or this shape. For snowflakes, as you know, they can be all sorts of shapes and sizes. They can have different amounts of water. They flutter as they fall to the ground. So it makes it quite a challenge, but it's great to be on the cutting edge of research. And we snow experts here that are working on this project are really looking forward to the data that we get from GPM. And we hope that you're just as excited about the mission as we are.
Wonderful. Thank you very, very much. Next up, we're going to hear from Riko Oki. She is from the Japanese Space Agency and is the GPM scientist for them.
So thank you. So I'm very happy to be here today to meet all of you. So, and I would like to introduce our expectation for GPM from Japanese point of view. So, so Japan is located in East North Asia and affected strongly by Asian monsoon climate. So we have 4 beautiful seasons. June is a month-length rainy season, and in autumn, every year, our life is affected by several typhoons approaching to Japan. In winter, a northwest monsoon wind from Eurasia becomes wet, blowing over Japan Sea and bring a lot of snow in Japan seaside along the central mountains. People in not only Japan, but also in Asian countries in Southeast Asia live with the blessings of monsoon and its rain. But at the same time, we are exposed to danger by water-related disasters. Actually, the most deaths are because of water-related disasters among natural disasters, not because of earthquakes or others. So, and the next movie shows the detailed 3-dimensional distribution of rainfall inside typhoons, was firstly observed by the observation of precipitation radar on board the TRIM tropical rainfall measurement mission satellite that launched 15 years before GPM. So, and the dual frequency radar called DPR has a new K-band channel which can detect snow and weak rain, and for rain rates, more accurate estimates can be expected using information from dual frequency observation. So, and the next animation shows the annual change of rain and snow area on the globe. We can see the seasonal march of rain systems like this. So rain band moves between north and south, and GPM observation will expand to 65 degrees in latitudes from south to north. The combination of DPR and GMI will observe liquid and solid precipitation particles from the tropics to the mid and high latitude. So precipitation is one of the most basic and important environmental elements relating to our daily life. So information of global precipitation, which will be delivered in near real time, will be utilized in various areas such as flood, drought warning, agriculture, weather forecasting, and global warming research. So we are waiting in expectation for the GPM launch. Thank you.
Thank you very much. We're going to move into some Q&A now for our first three speakers here. If you have a question, this is a good time to move to either of the aisles here. Or if you're online at home, you can also be asking a question using the hashtag #AskNASA. So we'll go ahead with our first question here.
Okay, hi. Now this question.
Can we have our three speakers come up?
So this question is from @ShayWoo. Just following along. And it's a question for Ramesh. And what he said is, how does the salty satellite fit into this? What he means, I think, is how does Aquarius fit into this?
Oh, okay. That's a good question. No, Aquarius measures sea surface salinity. And you can ask, how is that related to the water cycle studies that we're doing? Very simple. Salinity determines how much evaporation has taken place from the ocean surface. So if we can simultaneously measure salinity and through that evaporation, and also then measure precipitation from TRIM and GPM, then we can determine E minus P, evaporation minus precipitation. That's the total amount of water vapor that is getting from the ocean into the atmosphere. And so from the atmosphere, some of it will condense out as precipitation, as clouds, and some of it will be transported over land, etc. So this is the beginning of the water cycle. So that's why I think it's a very important companion instrument to TRIM and GPM Aquariuses.
All right, guys, don't be shy. If you have a question, come on out to one of the aisles here, and we'll go ahead and get going.
I got another one, but yeah, queue up just behind me if you do have one. Okay, this is for Riko Oki. And what's the difference between the scientists, I think they mean the researchers, in Japan versus the scientists in the United States? I'm sure they're all lovely.
Can I answer in Japanese? Okay. 雨をもたらすシステムというのはものすごくそのグローバルに共通性がありつつもローカルな特徴がとてもあります。それでやはり日本の研究者はその先ほどご紹介したようにアジアモンスーン、特にアジア地域でヒマラヤからですね、それからインドであるとか、それからフィリピン沖であるとか、台風であるとか、その日本に関係するようなそのアジアの雨の研究をしている人が多くいて、で一方でアメリカの研究者の方たちは見ていると、やはり南北アメリカ、特にブラジルなんかの研究は特に精力的にされているような気がして、その雨のローカル性についての違いが私にとってはまあ面白く感じられてますね。
In Japan, usually the precipitation, it's a global, but in Japan, they study more on the local, especially Japan, around Japan and Asia area. But in America, scientists study more on the North America, on South America, Brazil, and so on. Is that what you answer?
So for me, the differences of
so there's a differences there,
Can I just add that the Japanese and the U.S. science teams, we do work together We are all in this mission together, and we're trying to, even though there are separate teams, we work together and we meet together about once a year.
Okay, we'll take our next question from over on the side here.
I heard about the weather applications for this data, but it seems to me that it would also have significant impact on planting. Farmers, they would have a lot of interest in knowing this precipitation in more detail, the kind of detail that GPM is going to provide. Is there any effort being made to disseminate the information to those sorts of recipients?
Yes, this data is freely available to all the participants. Anybody can get hold of this data. The important thing actually is that NASA is a research organization. Originally, the requirement was that we release the data 72 hours. Very early on, we found out that, we surmised that nobody wants to know if it rained 72 hours ago, so we made a lot of effort to make sure that the data is available online in near real time. And many entities get hold of our data in near real time.
Thank you.
That answer your question?
All right, just a reminder for our online audience at home, if you have a question, you can ask it using the hashtag #AskNASA. We're going to go ahead and take our next question here in the room.
Hi, this question's for Gail on GPM. I was curious about the K-band. Will it be possible for the K-band to detect any amounts of pollutants within the precipitation in, let's say, heavy toxic areas around the world?
So the Ka and Ku bands on the dual precipitation radar are designed specifically for the sizes of raindrops. Aerosols and pollutants are much, much smaller. NASA does have other satellites that are taking these types of measurements, but they will not be on board the GPM mission.
Thank you.
All right, do we have another question here in the room?
Thanks very much for this presentation so far. So I grew up in Vermont, and I saw a lot of what happened in Irene. I just wanted to know, had GPM been up and running, how might have you liked to have seen that happen differently? What would you like to have seen happen?
So I guess I'll answer that as well. If GPM had been up there, we would have hoped to have been able to get the GPM core satellite to overfly it, and then we would be able to have the three-dimensional structure from the storm. And then we could put that in the models that they're using post-processing of Irene to better understand the storm and to find out whether the intensity would increase or decrease. One of the other things with all the constellations is we would be able to tell you very near real time, which is about 1 to 3 hours after we collect the data, how much rain accumulation has actually occurred, so that the local populations and the operational communities can say, all right, evacuate these areas.
All right, wonderful. We have another question here in the room.
Hi. As you move more towards real-time data release, how is this fitting into the predictive analysis? Is the data starting to feed back into modeling that the National Weather Service or NOAA are doing?
Absolutely. Yeah, NOAA is a very important partner in all of this, and we have several team members from NOAA on our science team. And actually, let me go back. When we first launched, we had very modest dreams, and we didn't even know if we can study hurricanes with it. And lo and behold, not only we could study it, we could, as explained by Rico, we could CAT scan the internals of the storm. And now 600 times a year, agencies across the world, they use TRIM data to locate the center of hurricanes, for example, just to give an example. So yeah, it's very much in use, and the importance of it is being realized every day, and we are getting a lot more attention from the weather services from around the world. The NOAA and the Japanese meteorological are especially engaged, but many other agencies around the world are also getting engaged. For example, the European Center.
All right.
Hi, my question is to Gail. I just wanted to know what's the swath size of the data for the satellite? And another question, what's the spatial resolution of the data we are providing? And another is the near, you're saying like it will be a near real-time data. So what will be the time lag between when it's come to the users? Or will it be available for the researchers to get those hand of the data as it comes?
Thank you for asking that question because I wanted to answer that question. I wasn't able to put it in my presentation. So as this video is showing, the radar images, the inner swath one is about 145 kilometer swath. And the radars actually are cross-track scanners, so they go back and forth like this. And the KU has about a 245 kilometer swath. The radiometer, which will show up in just a second, has 880 kilometer swath. The resolution of these, the best resolution from all the different channels here is about 5 kilometers. So, you know, if you go out and put a rain gauge in your backyard, it's only measuring a very small area. So this is like a 3-mile diameter from your neighborhood, which is really kind of measuring the local scale of precipitation. Last question. Oh, yeah, it was the near real time. So for the radiometer, for the passive one that has a wider swath, we hope to be able to put the data out online within an hour after collecting it. And we collect each cycle of the overpass, so each cycle is about 90 minutes. So the earliest data would be 1 hour, it might be in 2.5 hours. For any products that include the radar data, they're going to be about 3 hours after we collect them. So it's near real time. It's enough time if the operational people and the disaster prepared people are looking at our data that they could go out and tell their communities if they're looking at it. It's up to them to come look at it.
Wonderful then. Do we have any more online questions? All right then, any other questions here in the room? Okay, we're going to go ahead and move on now then. Thank you guys very much. We've got a few interesting things that we have learned about the mission and other things related to rain and waterfall and everything and precipitation. So without any further ado, here's a couple of fun facts. All right, without any further ado, I want to introduce our next speaker here. This is Art Azerbarzan. He is the project manager for the GPM satellite here. So without any further ado.
Thank you, Jason. Good morning, everyone, and welcome to Goddard Space Flight Center. Another fun fact for you, Goddard is the first and the oldest center of NASA. Was established in 1959. I've been a project manager of GPM since 2006, and Candace Carlaw, our deputy project manager, we've been together here since then. and we've had a lot of fun so far. As you look at our logo in the bottom here, and then as Gail explained, we picked that logo, the shape, because it's a true shape of rain. If you look on the internet, and if you Google true shape of rain, you realize it really does not look like teardrop. Now, you heard from Gail and Rico and what we're going to accomplish in this mission. Now, how do we do that, and how do we implement this? Well, we couldn't have done it with our Japanese partner, and this has been a very strong partnership, and he's been a great success for us. Now, GPM is comprised of 4 elements. One of them is the Data Processing Center, known as Precipitation Processing System, or PPS, capable of putting a global products within 3 hours. The second one is a ground validation is another element. That's another international partnership which gives us a capability to measure the satellite data and compare it with ground base. Mission Operations Center is for operating the core observatory that's also located at Goddard across the facility. The last is the core observatory development at Goddard. A cross calibrator, as Ramesh mentioned, for the entire constellation of the GPM. Now, where are we with the GPM development at Goddard? We are in the middle of a test program. We should be finishing that by the end of summer. There's a quick animation that's coming up that's showing how our satellite is put together. I wish we could put all the satellites this quickly together. We could launch more of them. Unfortunately, it's not that quick. We started the core observatory with the qualification of flight structure. We used a centrifuge at Goddard to perform that test. In parallel, we developed a lot of components, solar arrays, and other needed things that we procured either from private industry or we built it. Now, the core observatory does have 2 very sophisticated instruments on board, as you have heard. The dual frequency precipitation radar, known as DPR, is provided by our partner JAXA for this mission. And the other one is a GPM microwave imager, which is also known as GMI, and is Ball by Ball Aerospace, and Don Figgins here is representing Ball. And we are very proud of the performance of this instrument. GMI has 13 channels. It covers 10 gigahertz to 183 gigahertz, which detects rain to snow to ice, and is one of the best calibrated radiometers in its class. GMI was delivered to NASA in February 2012 and was integrated on the observatory the month after in March. And the DPR was delivered to us in March 2012, and we integrated that on the observatory shortly after in the month of April. Now, after completing the assembly of the spacecraft, we prepared for environmental test program. As you saw in the video, first we tested in the thermal vacuum chamber, and this exposed it to the space environment that it sees by doing a thermal and a vacuum of the space. And since the door of the chamber is on top, we had to lift the spacecraft into the chamber. Following the completion of that test, we prepared it, we brought it back to our clean room, and we prepared it for electromagnetic interference testing, which you see in a visual here, and that test is currently in progress. After completing the test program, we'll ship to the launch site, but at the end of October, early November 2013. We ship via C-5 Air Force aircraft. We refuel in air and land in Kitakyushu, Japan. Once we land, we offload to a barge, and from there, we transport from Kitakyushu to Tanegashima Island. We plan to launch within a 2-month window in 2014, which starts on January 24th. Now, the launch animation shows the the spacecraft on the H-2A rocket launching from Tanegashima Space Center. Now, following the separation from the second stage, the observatory is placed in a 400-kilometer orbit in a 65-degree inclination. It is roughly about the same location as International Space Station. This is another fun fact for you. But you can't see it when it goes across because we're too small. Okay. Following that, once we're on orbit, we start our deployments. We do the solar arrays to be power positive. Then we do a high-gain antenna to downlink the data. And then we deploy the GMI reflector and start rotating them. And then we activate the DPR. And after that activation is complete, it takes us about 60 days to go through a checkout period and hand that over to the operation teams for the science observation. That's all I had for you. Jason?
Indeed. Next up, we're going to hear a little bit from from the project manager for JAXA's contribution to the spacecraft here, and that's the Dual Frequency Precipitation Radar, or DPR, and this is Masahiro Kojima.
Good morning, everyone. My name is Masahiro Kojima. I am JAXA project manager for DPR instrument on GPM Core Observatory. DPR project team was established in JAXA Tsukuba Space Center in 2003, and since then I have been managing the project in JAXA. DPR stands for the Dual Frequency Precipitation Radar. It is the only one space-borne dual frequency precipitation radar in the world, and it will play a key role for GPM mission. DPR consists of the KU band radar and KA band radar. KU PR is similar to the precipitation radar on TRIM satellite. KA PR is a new development. It has a very high sensitivity, so it can detect 0.2 millimeter per hour rainfall. You can stay without an umbrella in the 1 millimeter per hour rainfall. So 0.2 is a really very weak rainfall. One important feature of the DPR is its high sensitivity and accuracy, but another important feature is that KU band beam and KA band beam is precisely matched so that we can observe the same rainfall in two frequencies simultaneously. And this is very important to improve the estimation accuracy of the rainfall rate. DPR adopts phased array technique, and it does the beam scanning in cross-track direction electrically. DPR has been designed, built, and tested in Japan. All the DPR system test was performed at Tsukuba Space Center. During the test, we experienced Great East Japan earthquake on March 11, 2011. Fortunately, there was no human loss in Tsukuba Space Center, and there was no severe damage to the DPR, but our test buildings and test facilities were severely damaged. And also the social infrastructure, such as the power and water supply and the transportation system, was lost. So we needed a tremendous effort for the recovery of the damaged buildings and facilities so that we can restart the DPR testing. Eventually, we completed the DPR testing in March last year, and DPR was shipped from Tsukuba Space Center to NASA Goddard Space Flight Center and officially delivered to NASA at the end of March last year. And after the delivery, we continued to support NASA for DPR handling, inspection, and performance testing. I'd like to introduce you the DPR logo. I wanted to give a Japanese flavor in it, so I selected this logo design. Calligraphy is one of the traditional culture in Japan, so this DPR logo represents our strong Japanese spirit towards the success of the GPM mission. GPM will be launched in early 2014 by Japanese H2A launch vehicle from Tanegashima Space Center. H2 launch has been successful in all the past 22 launches. The launch site is at the south end of Tanegashima Island, and Tanegashima Island itself is located in the south end of Japanese islands. This island is famous historically because the gun was firstly introduced to Japan in 1543 by Portuguese. They were on board the Chinese ship, and the ship was stranded near the Tanegashima Island. Lastly, in North Japan, we stock the river with baby salmons for the future salmon harvest. Baby salmons will go to the Pacific Ocean, spend several years there, and return to Japanese rivers as grown up for making babies. And DPR is a kind of baby for me, and I have released DPR to the United States. And I'm very happy that the DPR will come back to Japan, grown up as the GPM observatory, and will be launched by Japanese rocket. Thank you.
Wonderful. We're going to move into some Q&A here for our online audience here at home. If you are going to be asking a question, please use the hashtag #AskNASA. If you're tweeting in Japanese, you can also ask it using #AskJAXA. That's JAXA. If we can go ahead and have Masahiro and Art come on up here. We're going to go ahead and take questions. If you're in the room here, remember to move to the aisles. And we'll go ahead and get started with our first question.
This one is from @cat42. And it's, I want to know essentially more about the testing of the satellite and the assembly. I think it's a question for Art. Should we just talk more a little bit about how the pieces moved from place to place? I know you sort of did that, but just why were they sort of moved from Japan back to here and back to Japan?
Well, the reason this is obviously is an international partnership, and if you would have done this, mission alone, it would have been very costly for each country to do it alone. Therefore, the contribution with the JAXA, which launched services to us, and with the DPRs, in order to save taxpayers' money, we did this collaboration, and then shipping it from here to JAXA to launch it on H2A does save both countries money in accomplishing this mission.
Okay, next question. Do we have one here in the room over there?
Yeah, this may be a stupid question, but the reflector appears to be on the top of the satellite, and it is because it's measuring in microwaves, does the body of the satellite and the other receptors block its transmission at all, or is the microwaves just pass through the body of the satellite?
Okay, so the question is, well, the reflector is on top and rotates. However, it rotates all the way across, but we only use about a 800 or so, 880 swath, which does not go across solar rays on the body of the spacecraft. That data is available, but we do ignore that data, extract that data, so it does not corrupt the data.
Great, thank you.
All right. Do we have another online question here?
This question is, how does the data get from the satellite to my computer?
Okay. As we talked about, we have a mission operations center. Okay, so the satellite has a high gain antenna, which is hidden behind the sea of the social media, and that is a main point for us to take the data to the ground. From satellite, from the high gain antenna goes to a TDRS. We have 3 TDRSs, and we are continuous communication with the TDRS throughout the mission. That's one reason we can give you a near real time, with less than an hour, the GMI data. Now the data from the TDRS goes to White Sands in New Mexico, and the White Sand, the data comes back to the Mission Ops Center, which is right across the street from here in building 32. And then from then, it goes from there to the PPS. The science data gets extracted, goes to the PPS, and gets processed, and then gets distributed via the PPS system, the Precipitation Processing System. And that we talked about, that whole length operation, collecting all that, is within 3 hours. Now, 3 hours is a combined, consolidated, the product, the global product that we put together within 3 hours. But the GMI radiometer is within less than an hour. That could be real time.
Do we have another question over on the other side over here?
Yeah, sort of following up on that, actually, you kind of addressed this with that last question, but I was just going to ask how much, once the satellite launches, what's actually going to be happening on the ground here at Goddard, and how much of the, mission operation is divided between, here or somewhere, with JAXA or anywhere else?
Okay, the way it will work is Candace and I will split. Either she stays here and I'll be in the control room in the Tanegashima Space Center. And once we launch, the Ground's Mission Operations Center is always in contact and online even before launch. So our team will come in here about 7-8 hours before launch. They will check into Mission Operations Center, and we also check into the control center within like a couple hours of the launch. And then once we have launched, separated, the mission operation basically takes over from that point on, and observing and commanding the spacecraft once we separate it, and the high gain antenna is up, deployed. We do have Omni antennas that we do communicate during the ascent before the high gain comes up, but we only do that for the first part of the mission before high gain antenna comes up. But that's how the Mission Operations Center gets involved. But in the first 60 days, it takes us several days to first check out the spacecraft. Then after that, we deploy the GMI, the reflector, and then after that, we activate the radar. And as I explained, it takes us 60 days for us to get through that process, and then we completely check out the spacecraft and hand it to mission operation for science observation.
Wonderful. Just a reminder for our online audience here at home, you are able to ask questions using the hashtag #AskNASA. We're going to take another one here from online.
Okay, and this is from @HappinessWins, Heidi. It's actually not quite a question, but she really loves the DPR logo and how it's been developed. And I know that JAXA is very proud of the logo. Kojima, was that something that JAXA pulled together? There's an artist I know who developed it.
Yes, there is an artist who is a modern calligrapher and also the designer. And there were actually several designs, and we discussed internally, and also we discussed with Japanese scientists, and lastly we decided this DPR logo.
Wonderful. Do we have another question over on the other side there?
Okay.
Oh, one second.
Well,
We'll take another online question here then.
And it's another question for Kojima. It's about how did the Japanese earthquake affect this really delicate space instrument?
Yes, when after the shake, about 1 or 2 hours after the shake, I went to the satellite test building, and I was very shocked that the building was severely damaged. And although there were some after shake continued, we went into the building to see the state of the DPR, and I was very relieved that although some dust were over the DPR itself was not severely damaged, so very relieved.
Just to add on one more thing, it's like an earthquake is something that goes all parts of GPM. The most severe one is in Japan. We had one in Maryland during the integration of the satellite, and then we had one in California where some of the components was being tested. Actually, our gyroscopes that's on our spacecraft. And then actually it was under test when the California earthquake happened, and it detected the event while doing the test, because that's what gyroscopes do.
It sounds like you guys will be happy once it's finally safely in outer space.
We have a question over on the other side now.
Hi, my name is Jason Sanchez. I'm online Quarkity on Twitter. I have a question. This is actually a little different than the GPM.
Could you speak louder a little bit?
Yes, sir. This is a different question than the GPM questions, and this is more so towards the future launches, question for NASA and also for JAXA. Now that in South America, Bolivia has started operations for mining pure lithium in the salt flats in Salar de Uyuni. Do you think there will be a realizable future on the fusion-driven rocket now that there's so much lithium at stake, since they're finally starting to harvest this material, because it uses pure solid lithium to potentially, theoretically, use this material to launch?
Well, even though we're supposed to be rocket scientists, but we don't have any actual rocket scientists in the room that can answer your question. But all NASA people are rocket scientists. But that's a question really for NASA headquarters, and also especially for the Kennedy Space Center, which handles all the launches and what the future is.
If you tweet at NASA Kennedy, they should be able to get you an answer to that. So,
thank you.
Definitely. Do we have another online question here?
I have an old school paper question from someone too shy to come to the microphone. So, and it's, okay, should have read it first. What is the coolest test the satellite goes through before launch? And coolest has little marks, finger marks around it, so I don't know if they actually mean coldest or the one you consider the most cool.
Okay, well, I'll answer both. So, coldest is in thermovac chamber that we run our satellite. But actually, the way our spacecraft, as you noticed, all these, duct tape type material blankets that we have, that keeps us as spacecraft warm. And there is a reason why it's that duct tape material, because most of our components on this observatory is on the outside, and therefore we have to use a different type of blankets, which is not orange. Traditionally, you've seen orange blankets on all the spacecraft, but ours is duct tape, and there's a reason for that. But because we have those blankets, it does see a very benign environment. But for the coolest test, I guess I'll pick the cool test that we do on orbit, which we didn't talk about. Now, we're in a 65-degree inclination, and so the sun moves all over the spacecraft. If you're familiar with some spacecraft called sun synchronous, those are the polar that go north-south. Sun always stays the same side. But for us, sun comes from one side, goes to the top, and moves to the other side. But so, in order for us to avoid the sun to heat up, because we have to design the spacecraft that one side is cool and one side stays the warm side. So every 30 days, when the sun moves to the top, we turn the spacecraft 180 degrees around and fly backward for another 30 days until the sun goes to the other side. And then we turn again, and then sun comes up top, then we turn again. So that's one of the coolest things that we do. And we also do calibration. We point at the cold space, stare, and for a long time, and calibrate our instruments.
Wonderful. I personally have a question here. You're the project manager for this and everything. What keeps you awake at night? What's the one thing that you're really, really worried about with this mission, and that once it's on orbit and everything, you'll stop worrying about?
It's hard to say. I think all the stuff that kept us awake so far, most hardest ones are behind us. We finished thermovac, but there are always an element of surprise. As much as you have planned, as much as you have practiced, as much as you always, we do a lot of lift operations. We do a lot of moving around on the spacecraft. And, until we stop and put it in the shipping container, I think we're still going to keep us awake at night.
All right, then. Do we have any other questions here in the audience? Do you have a question, sir? Okay.
Hi, my name's Scott. Just a quick question. How long is the mission scheduled to go for?
Our mission is designed for 3 years, and we have fuel on board to carry us for minimum of 5 years. Now, since we're launching in early 2014, we passed the solar max affair. So therefore, our recalculation says, under worst case condition, the fuel should last us about 7 years or so. Now, as you know, these are all worst case on top of worst case on top of worst case. And TRIM was supposed to last only 3 years. And then so I think the bar is set way too high for us and expects us last more than 15 years. But minimum, we expect, as on the worst case condition, for us to be at least 7 years.
Okay, thank you.
Wonderful. Do we have another question over on this side here?
Hi, just wondering about lifetime costs of the project and how secure that funding is, given track record on some other projects.
The life cycle costs for this project, I think, is on the NASA website, is about $933 million, and the sequestration has had no impact on our mission. One thing I can say, but this 933, you have to remember, covers the 4 elements that I talked about. It's not only just a satellite and a build. Satellite and a build is a fraction, a third, or a fourth of that. But a lot of testing, ground system, mission operations, and operations on orbit, which is PASS, which makes up the total life cycle of this mission, cost of this mission.
Wonderful. We have a question over here on the other side.
Yes, I was curious if you were able to use any of the data collected by the sensors during the earthquake to calibrate any of the sensors. Did you get anything useful out of the event?
Well, when the earthquake happened, all we know is gyros are functioning properly, which was in California, which is did see a seismic event, and then this was sort of correlated with the numbers that was but that's not the purpose of those having those components on the spacecraft. It just happens to have that feature that it does catch the earthquakes as well, if it's sitting on a bench somewhere being tested.
All right, wonderful. We'll take a question over on this side now.
Hi, this is for JAXA. Once GPM is launched, how far in advance or how much notice will you get in noticing a typhoon or a monsoon over your region? How quickly would you be able to react and get the information out to your people?
I think that as Mr. Zabadin and other scientists explained, GPM data is collected and processed in near real-time basis, and those near real-time data will be transmitted to Japan also, and those data will be used in the Japan Meteorological Agency also, and they use those data for the weather prediction and also the typhoon prediction, those kind of activities we are planning. Okay.
Wonderful then. Is there any other questions here in the room? All right, let's thank our two folks here for answering all these wonderful questions. All right. So a little bit earlier during Art's presentation, you saw a clip of the launch animation and so on, but we're going to show you the full launch sequence here, the full animation and everything. It's really pretty to watch, but it also really shows you all the different moments during the entire launch to orbit cycle. So.
4, 3, 2, メインエンジンスタート。メインエンジンイグニッション。SRBA 点火。リフトオフ。SRBA イグニッションでリフトオフ。カビア搭載した H2A ロケット13号機は平成19年9月14日。
Wonderful. So hopefully early next year, everybody will be watching NASA TV and tuning in and to see that happen in real life. And so that'll be a pretty good momentous occasion to get the satellite on orbit and begin collecting data and everything. So without any further ado, we're going to move on to our next speaker. We have Peter Hildebrand. He's the director of the Earth Science Division here at Goddard Space Flight Center. And he's here to give you a little bit of the Earth science perspective on where this mission fits and everything.
Thank you, Jason. It's thrilled to be here, and I'll just say a few things about how cool a mission this is. I mean, it's just really amazing. And the other thing I want to leave you with is the importance of the international collaboration that has made this possible, but also I'll say a whole bunch about TRIM, because TRIM was launched in 97. That's just a few years ago, and it's still up there. It was supposed to be operating for 5 years, isn't that right? Three? Okay. But that was the worst case scenario. And then you hope things work better. And then it turned out to be so important as an international collaboration and a scientific tool that we figured out that if the satellite was moved higher, away from the drag of the atmosphere, it would last longer. Well, it's still doing it. In fact, this actually took a campaign by researchers in the community to do it. I mean, NASA was struggling with it and couldn't quite make the decision that we were going to run it so long as this, because it costs a lot of money. But there was a big campaign from university researchers to keep that satellite running. So I want to talk a little bit about the science that happened and about the human impact, and then about the importance of the international collaboration, which is something that started in this particular case with TRIM. That was back before I even came to NASA 15 years ago. There was discussion about how to build TRIM and what was it going to look like. So it's a long-term collaboration that has involved the Japanese and the United States researchers. Now TRIM is just one of, and then GPM, which is going to be launched, it's just one of a whole bunch of missions that are operating right now. And we've seen those animations before of the whole slew of satellites. There are a couple dozen of them up there. Here they are. And you can see TRIM going in front of the Earth there, and a whole bunch of other satellites. The reason there are all those different satellites is that you really only can make measurements about one or two types of things on any different satellite, because they're very complicated instruments. Because on TRIM and on GPM, we have a radar that's looking down from the bottom of the satellite, and we have a radiometer that's scanning out ahead of the satellite to make these measurements. And that's a big satellite. If you want to know how big it is, it would just barely fit in this space right here on this stage. I don't know if this is tall enough to take it. I'm not quite sure. Art, would it fit? I didn't think so. I was sitting there wondering. It would go up above the roof. It's so big. This is the size of a fire truck, and it's getting launched into space. Now, what was so interesting about TRIM and that we pushed so hard to keep it going? If we could go to the next animation, this is another animation we've seen before. The things that we noticed because of this is that for the first time, we had an idea of what the precipitation was like around the Earth. And so you can see this band of more precipitation around the equator, and it moves north and south. Actually, what it does is it moves away from where the summer is, because the summer hemisphere is a little more powerful, and it pushes that intertropical convergence zone away. The other thing that we measured for the first time is you can see these bands going from the equatorial regions towards the poles, like here and there and up there. Those are the precipitation tracks. And we didn't know exactly how they operated. We didn't know exactly how all this moved when there was an El Nino or some other big oscillation of the Earth's atmosphere. So we learned a whole bunch about global precipitation and how that changes with time of year and changes with the big oscillations of the Earth's atmosphere. And it helps us understand a little bit about how things are going to change as the climate changes. Now, why is this so important? Well, these precipitation measurements, this is where we get the water for plants and animals to live. We humans depend on this. And by knowing this, the amount of precipitation, we can calculate we can calculate sort of applications products that have to do with flooding. That's been mentioned before. We can also talk from coupling that with other instruments we can make measurements of the health of crops. And by knowing how healthy the crops are and where the flooding is, we actually create a famine forecast product that we give out to USAID and other government agencies, and that's used to reposition food supplies to places famines are going to happen but haven't quite happened yet. And it's all because of things we've learned starting with TRIM and moving on to GPM. So there's a whole bunch of really important stuff that starts with the science and moves all the way through to these applications products that are things that we in NASA deliver to the nation and the world that are of use to human society. But to get back to the international collaboration, this thing wouldn't have happened without the collaboration that's gone on for so many years between Japan's JAXA and the Japanese scientists and the United States NASA and the United States scientists. This is to disclose, this is something that's been going on now for about 20 years, this project. And it's gone to make TRIM happen, now GPM, which is going to be bigger and better and answer more questions. And it could easily go on into the future. I can't imagine the international collaboration will be over at the end of GPM, and no one knows how long that will last. I think a little longer than the planned minimum. How many years, Art? What's the minimum operation for GPM? Minimum 7 years. I think it might go a little longer. Anyway, thank you very much.
Wonderful then. So we're going to go ahead and move into some question and answer sessions. For our online audience at home, just one more reminder for you all. If you have questions, please ask them using #AskNASA as the hashtag. If you have a question here in the room, if you can step on out to one of the aisles to either of the microphones, and we'll go ahead and take our first question over here on the left.
Hi, what's the biggest difference between the TRIM mission and the GPM and, from a measurement perspective?
Two major differences. One is TRIM only went 35 degrees north and south, so we basically were getting equatorial and subtropical measurements up to just in the beginning of the temperate zone, whereas GPM is going to go up to 65 degrees. So that gets us up into areas where Gail Scafronic Jackson's expertise kicks in measuring snow, which is so important for so many parts of the world, including the deposition of snow and the buildup of snowpack to run off down the rivers for water resource. So a major thing there. The other thing that's different is that it's a dual frequency radar, which tells us a whole lot more about the drop size distributions, hence how much water is really there in the clouds.
Okay, thank you.
Actually, there is one more difference, and that is the radiometer has high-frequency channels, 183 gigahertz channels, which are very important, again, for measurement of snow. Now, also the antenna is much larger, so we have a much smaller footprint, and that is very important because when we do it passive microwave, we need to have a beam completely filled, so the bigger antenna is also, so that's the big difference.
Thanks, Ramesh. Those are some of Gail's most favorite instruments,
Antenna
those high-frequency
reflector.
channels.
Wonderful then. We have another question over on the right over here.
Yes, my name is Katie Preston, and my Twitter is RVA Green Rev. And my question is not necessarily particular to the GSM and TRIM, or GPM and TRIM missions, but more generally about the Earth Sciences Division of NASA and their importance in true science-based knowledge about climate change and the impacts. I work with the faith communities on environmental issues, and there's a lot of unfortunate debate about the realness of climate change, but I think the value of being here today is learning more about how NASA is using missions like this and other programs within Earth Sciences to give us the science behind climate change. And so I'm wondering if you can talk a little bit about how these missions will feed into helping us better understand the impacts of climate change, particularly when it comes to precipitation events and, like we talked about earlier, the flooding that comes from precipitation and all of the detrimental impacts of the ravages of water.
Thank you. Great question. First, about the agency, NASA is a model for how agencies should treat its scientists. We were told very clearly when the climate change debate started heating up that our job was to communicate what we knew honestly to the public. Now, we're not here to talk about policy. We all have personal ideas about the policy. But we are here to communicate what we know about climate change and the measurements we make. So that's what we do. And there's no question about climate change from our point of view as scientists or about human causation. And we unabashedly say that as NASA scientists. And just the way it is. That's what we measure. The importance of GPM and TRIM, though, is the ability to develop all these human applications products that are so important and are delivered all over the place, that have to do with flooding, have to do with drought, have to do with changes in ecosystems, and the ability to grow crops in different places, knowing where crops are healthy and things like that. So GPM is a very important part of that, and it's something we communicate as best we can. Thank you.
Wonderful, then. Do we have another question over here?
Yes, hi, from chrishaber.com. And I was asking something along the same lines. I was wondering if another spacecraft of similar design and construction could be used to fly north to south and to gather information on the polar areas for climate change.
A great question. Could you have a polar orbiter so you actually get the whole Earth? And the answer is that the design of the orbit for any satellite, and actually you'll see some polar orbiters there, is dependent on where you want the satellite to be and how you want its measurements to be made versus time of day. One of the problems with the GPM, the precipitation measurements, is you want updates on a 3-hourly basis or even better. And so you choose an orbit that has some precession around the Earth, that is, the satellite has to move with respect to the spot below it on the Earth. And if you choose some polar orbits, it always goes around the same spot all the time. So you see the same time of day, and we don't want to do that. So the orbit design is a rather complicated aspect of what you want to measure and how you want to measure it. But good question.
Well, I guess more of the point of what I meant by the question was, could it be used, could a device such as this one be used to monitor the precipitation or in the polar regions to gather data on climate change?
The answer is yes. If you had a polar orbiter with these measurements, you could make measurements over the polar region, but you might then not be able to make measurements other places at different times of day. So that's part of the trade-off, and I think that Art might have a comment to make there.
I just want to just point out one thing you asked about the orbit. Well, the constellation has many polar orbiting, so we get that data as well. The reason the 65-degree was decided versus 35 for TRIM, if you look in the map of the Earth, there's not much land coverage. Rain over land was not covered. So by going 65 degrees, we serve two purposes. One is that we can cross-calibrate all the polar orbiters because we go over the track all the time, and that's how we bring the calibration and adjust the data and make sure their data is adjusted so it's more accurate. And then we also can collect. If you go look at the map and look where 65 crosses all the continents. You see that we're going to be covering more land and more coastal areas of where the rain is going to occur, where the most important part is, where all the hurricanes and everything affects the coastal area.
Wonderful. Just a reminder for our online audience at home, if you have a question, you're welcome to ask it using the hashtag #AskNASA. So I think we're going to go ahead and take an online question. So Aries?
Okay. This question's for Peter, and it's going to make you groan a little bit, so sorry. But why is NASA studying Earth science? We should be looking at other places, not the Earth. My apologies. Sorry.
Well, there are all sorts of opinions about what NASA should be doing and shouldn't doing. I happen to be an Earth scientist. I study the Earth as a system, so that's our thing. NASA also, though, is doing a lot of study of other things. There's heliospheric science division that studies the sun and how the sun varies and radiation episodes from the sun. There's an astrophysics division that built the Hubble Space Telescope and is going to build other space telescopes studying all sorts of things about the origins of the universe and things like that. And there's also a planetary division that studies the other planets in the solar system. We in Earth Science actually collaborate with them and the astrophysics folks on looking at finding other planets and the search for life elsewhere. That's a big thing. So we're kind of all over the place when it comes to science and using space to understand science. It's really a neat place to be.
Wonderful. We have another question over on the side here.
Hi, my name is Jim Acker, and I'm actually both a tour guide and I work with data of several types in the Goddard Data Information Service Center. And one thing, I have a comment and a question, because TRIM data, even though the TRIM orbit only goes to about 35 degrees, because the swath extends beyond that, you can get data to about 45 degrees, like up to about the US-Canadian border. My question was related to the polar. If GPM orbit goes to 65, is the swath actually going to go further north and further south by several degrees, or is it actually going to stop there?
A little bit, but Ramesh?
Well, that is the point of the cross-calibration. We spend a lot of energy in cross-calibrating the polar orbiters against the GPM core. So even though the GPM core is not able to go to the poles, the polar orbiters are, but they're tuned against GPM. So we are essentially getting the data of approximately same precision with the polar orbiters who can get there, but GPM core cannot. So that's
Will the GPM swath go a little bit further north than 65?
a little bit, not for the radar, but for the radiometer a little bit.
Okay.
But not to make a big difference. But our reliance, that's the whole point of the constellations is. See, even now we are able to get a coverage of 0.25 by 0.25 degrees by what we call a multi-satellite analysis.
Right.
We are, even though TRIM takes about 17, it takes a long time to get total coverage from TRIM. We are able to get that by cross-calibrating a large number of satellites, which are designed for other purposes, but we are able to cross-calibrate for measuring precipitation. So
I'll point out we have that multi-satellite data in Giovanni, so
yeah.
It's a good data product.
Yeah.
Wonderful. Then, do we have an additional online question?
Plugging your own project. Okay, I'm clearly the queen of the odd questions. How will this mission help us control the rain?
The first science job I had as an atmospheric scientist was working on a weather modification project. And that went on, that was a big area of research way back when, before my hair was this color. That's pretty much stopped. because we've found that there's just so much water up there, and you can move the precipitation a little bit by doing weather modification, but you really can't control the rain. So, great question, but unfortunately, I don't think we're going to do that.
Thank you.
All right, wonderful. That was our last question. Thank you very much, Peter. So on behalf of all of us here at the Goddard Space Flight Center and at NASA overall, as well as our partners at JAXA, we want to thank you guys for tuning in for today's broadcast. This ends our show here. Before we go, just a reminder that if you want to learn more about GPM, you can follow it on social media. On Twitter, it's at NASA_rain. And on Facebook, it's available at NASA Rain. If you are looking to follow along with everything else that NASA has going on, please follow us on @NASA. If you're looking for us on Facebook, you can find us at facebook.com/NASA, or you can also find us on NASA at Google+. Beyond that, if you have any other questions or anything, please feel free to tweet them into any of the accounts that are there, post them as a comment, and we'll be looking for those and to get you guys answers. If you want to find out about an additional NASA social events that are happening in the future, you can always follow us at nasa.gov/social or at NASA Social on Twitter. So thank you very much for tuning in today. As we close out today's broadcast, we do have one last little video talking about measurement and for good measure. So.
We plan our lives around rain. We always want to know when and where and how much. Not just for our weekend plans, but for how we make decisions about our safety and transportation, our economy.
Well, apparently we were talking out of sync with our lips, so it's ventriloquism, guys. All right, then. Well, at this point in time, then, we're going to go ahead and wrap up our broadcast. If there's anything else that you guys have questions on, our panel of experts will remain here for a little bit longer, and you guys are welcome to ask them. We also are going to continue on this afternoon with a tour of the testing facilities here at Goddard. We're also going to be able to see the spacecraft in the clean room, in some of the test facilities a little bit later today for those who are on. So if you follow along on all of the social media postings from our attendees today, we'll be able to really, give you guys that in-depth experience looking at the spacecraft and everything. So look out for more of those social media postings. All right, then. Thank you all for tuning in very much today, and look forward to seeing you all online again. So thank you, guys.